Hello everyone, it's Miss Thomas, and today we're going to look at some more theorems about roots. I know you are all very excited. So the first theorem is the conjugate root theorem. And it says, if p of x is a polynomial with real coefficients, then irrational and complex, which is just another way of saying imaginary roots, occur in conjugate pairs. So what this means is, and our sixes are kind of slopey here, but if you have 2 plus the square root of 6 as a root, then 2 minus the square root of 6 is also a root automatically. And if you have 3 minus 4i as a root, then 3 plus 4i is a root as well. So really it's just saying if you have a square root or you have an I, automatically the plus minus will be part of the roots. Okay, so we're going to see this in a problem similar to this. What polynomial equation has the roots of 2 minus 3i? So this is one root, and I don't know why that's floating up there, square root of 6. And the trick to this is you should know how to write polynomials from roots, but because there's this imaginary portion and because there's an irrational number, you automatically need to remember, okay, well if 2 minus 3i is a root, then 2 plus 3i is a root. And if square root of 6 is a root, then negative square root of 6 is also a root. So from that, we're going to write our linear factors. I'm going to start with the square root of 6 because it's easier. So x minus square root of 6, x plus square root of 6. So those are my two linear factors from those roots. Then I want x minus the quantity 2 minus 3i and x minus the quantity 2 plus 3i. So we want to make sure we do that minus because it's just proper mathematics. This is the entire root, so you want to subtract the entire root. But to simplify that, we're going to distribute that negative sign, so x minus 2 plus 3i, x minus 2 minus 3i. All right, so first we're going to multiply together our x minus 6 and our x plus 6. So x minus 6, or x times x is x squared. X times square root of 6 is going to be plus square root of 6x. And then minus square root of 6x. And then minus square root of 6 times square root of 6 is a 6. And then I'm just going to bring down my x minus 2 plus 3i and my x minus 2 minus 3i. Okay. So I'm going to simplify this. I have these like terms in the middle. They're going to go away. And I'm going to be left with x squared minus 6. And then that's going to be times all this complex stuff. So my advice to you is always, always, always multiply your complex roots together first, your factors with complex roots. So I'm just going to bring down my x squared minus 6. And then I'm going to distribute this. So x times x is x squared, x times a minus 2 is a minus 2x, and x times a negative 3i is going to be a negative 3ix. Then I'm going to take the negative 2 times everything. So negative 2 times x is a negative 2x. Negative 2 times negative 2 is a plus 4. And negative 2 times the 3i is going to be a positive 6i. And finally, I'm going to take my 3i and multiply it by everything. So 3i times x is going to be 3ix. 3i times 2 is going to be a minus, times negative 2 is going to be a minus 6i. And 3i times a negative 3i is going to be a minus 9i squared. So we obviously want to simplify all of this. There's a lot going on in there. So we want to look for our like terms. So x squared does not have a like term. We'll just bring that down. Minus 2x, and that's it for my just x terms. A minus 3ix, so you need the imaginary and the x, and a plus 3ix cancel out. And then we also have a plus 6i and a minus 6i. Again, those cancel out. We have a plus 4, and then we have this minus 9i squared. But even that can be simplified. So we're going to show you how that can be simplified. Because you should never have I raised to a power, because you can always evaluate it. So if you recall, square root of negative 1 is equal to I. So if you think about it, if you square both sides of this to get I squared, what happens is that the square root goes away when you square a square root. Negative 1 is equal to I squared. So this ends up being 9 times a negative 1. So 9 times a negative 1 becomes a negative 9, but then we have this negative up front, so it becomes plus 4 plus 9. Which becomes a 13. So now we want to multiply these guys together. So x squared times x squared, x to the fourth, x squared times 2x, negative 2x squared, x squared times 13 is 13x. A negative 6 times x squared is a negative 6x squared. A negative 6 times a negative 2x is going to be a 12x. And a negative 6 times 13 is going to be a negative 78. So combining like terms, we really only have the x's and the x squared. So we end up with x to the fourth minus 8x squared plus 25x minus 78. And that is my polynomial function with those roots that we started with. All right, so the next thing that we have is Descartes' rule of signs. If a polynomial is written in standard form, then the number of positive real roots is either equal to the number of sign changes between consecutive coefficients of p of x equals 0, or less than that by an even number, and the number of negative real roots is either equal to the number of sign changes between consecutive coefficients of p of negative x, or less than that by an even number. So let's just put that into action. Instead of trying to pull it apart, what does Descartes' rule of signs tell you about the real roots of 2x to the fourth minus x to the third plus 3x squared minus 1 equals 0. So for the positive roots, we're just going to go with this as is, and we're going to count the sign changes, keeping in mind that this is a positive term. So from here to here is one sign change. From this term to this term is another sign change. And from the third term to the fourth term is yet another one. So there are 3 sign changes in this original thing. So positive real roots. There will be 3 or 1. 3 because there's 3 sign changes, and 1 because if there's less, it's always less by an even difference. So then, to figure out the negative sign changes, I actually need to put in a negative x. So 2 negative x to the 4th minus negative x to the 3rd plus negative x squared minus 1 equals 0. So simplifying that, negative x to the 4th, because it's an even power, it's just going to stay even, or it's going to change positive. But the negative x to the 3rd will be negative once it's evaluated, because the negative times negative times negative will still have a negative product. So this negative and that negative makes this into a plus sign. And then negative x squared, negative x times negative x is still going to be a positive x squared minus 1. So our number of sign changes, because this is positive. From here to here, there's no sign change. From here to here, there's no sign change. From here to here, there's a sign change. So, negative real roots there's 1. So the reason there's 1 is because there's 1 sign change when I put in that negative x. And much like the positive, if it's less than 1, it's got to be less than 1 by even. Well, I can't take 2 away and I still have a root, because I'd end up with a negative 1. So there's definitely 1 negative sign change. So then you're going to want to graph this, and graphing can help you decide how many real roots you have and what their type are as well. So put it in your graphing calculator. When you put it in your graphing calculator, it's going to look something like this, which this is my negative root. So that checks out. And this is my positive root. So there's 1 positive root. Now, given that I have 1 negative and 1 positive, and my original coefficient, or my original degree was a 4, I know I'm going to have 1 positive root, real root, 1 negative real root, and 2 complex. To get the total of my 4 roots. So the next problem is your U-try. What does Descartes' rule of sign tell you about the real roots of 9x to the 3rd minus 4x squared plus 10 equals 0?